Hi, greetings and welcome back. So today's topic will be about how to design one preamp, and I'll be designing the low pass filters, single supply and dual supply from scratch. First I thought I'll be putting everything in a single video, but then people tend to avoid long videos, at least I do. So that is why I'll be dividing this video into three parts. First part will be about filter basics, the three types of filters and their basic knowledge. Second part will be about designing the circuits in easy EDA software, and third will be about testing the two boards. So the video will mainly focus on designing this single supply and the dual supply low pass filter board. Both are minus 24 dB per octave, and in the end we'll test these two boards. So without wasting any further more time, let us get started with part 1. So there are basically three kind of filters used for our amplifiers: high pass, low pass and band pass. Band pass is nothing but just mixture of high pass and low pass. So people think that high pass only deals with high frequencies, low pass only deals with low frequencies, and band pass only deals with mid frequencies, which is totally wrong. So ideally, high pass filter is a filtering technique which allows all the frequencies higher than the cutoff frequency to pass. Low pass filter is a filtering technique which allows all the frequencies before the cutoff frequency to pass, and band pass is just a combination of high pass and low pass. So let us understand more about these filters by plotting graphs or the response of these three filtering techniques. Okay, so to understand more about the filters, let us plot one graph using Excel. So in the right side, if you see, I have drawn one simple first order high pass filter circuit with one capacitor, one resistor, and the cutoff frequency is set to 265 Hz depending on the values of C and R. And I have also given the different calculations or the formulas that we'll be using to plot the graph. So first is our frequency, start from 1, then 10, 20, 50, and then selecting these two values. Let me have some, I don't know, maybe 200 values. Yep. Next up is our reactance. Reactance is nothing but a variable resistor which varies with different frequencies. So here the formula is 1 divided by 2 into pi, which is a function in Excel, into our F, that is this, into our capacitor, that is 6 nanofarads, 6 into 10 to the power minus 9. So this gives us our reactance at 1 Hz. We'll have the reactance for all the values, so till 200. Yep, so this is our reactance for all the different frequencies. Next is our total impedance. Total impedance is nothing but the square root of resistance square, that is 100,000 square plus the reactance square. So this is our total impedance. I'll do it same for all the values. Yep. Now comes V out. Before calculating V out, in order to simplify the circuit more, just think of this circuit as a simple voltage divider circuit. Okay, because this capacitor is nothing but a resistor which varies with different frequencies. So at different frequencies we have different values of the resistance of this capacitor. So using the simple voltage divider formula, we'll be able to calculate the V out. V in is 2 volts, V peak to peak is 2 volts. So the formula is pretty simple: 2 multiplied by the resistance, that is 100k, 100,000, divided by our total impedance of the circuit. So this gives us our V out, and I will do it same for all the values till 200. Yep. Now right away you can see one thing, that at low frequencies the value is very close to 0, but at high frequencies the value is very close to the input voltage, that is our 2 volts, right? And this proves that it is already acting as a high pass filter. Now response is just our 20 into log 10, which is a function again, V out divided by the reference voltage, that is 2 volts in here. Now this gives us our response in dB. We'll do it same for all the 200 values. Now what you're going to do is we're going to plot the graph by selecting this as the x-axis, the frequency as the x-axis, and the response in dB as the y-axis. Now we'll go to insert, we'll select one graph in here, this graph will be better, and that is our high pass filter graph. Let me do one thing, let me modify the graph a bit in order to understand or talk more about the graph. Okay, so I have marked the point where it's having the cutoff at minus 3 dB, it is having 265 Hertz. So here we need to understand one thing about the filter. The term high pass comes from it allows all the frequencies higher than the cutoff frequency to pass. That is why I have written pass all the frequencies higher than the cutoff frequency here, 265 Hertz. That is why it is termed as high pass, or it allows all the frequencies higher than the cutoff to pass. And not that it only deals with high frequencies, it can deal with any frequency. So here, as it's dealing with 265 Hertz, which is a low frequency, so it allows all the frequencies above cutoff frequency to pass, rejects all the frequencies below cutoff frequency, and that is why it is high pass filter. So just remember this point about the high pass filter. Now keeping this in mind, let us move into low pass filter. So now let us plot low pass filter graph. Only two things changes here. Now resistance is here and the capacitor is here, and the V out changes obviously because now the V out is 2 multiplied by XC, that is the capacitor's reactance, divided by the total impedance. So here we will make the change. So here we'll just change it to XC, and we will drag everything till the end. So you can see now that it reverses, or it's just the opposite of the high pass filter. Now at low frequencies it's very close to the V input, that is our 2 volts, and at high frequencies it's almost close to 0, and the response obviously changes itself up. And again in the same way we'll select the frequency as the x-axis and the response as the y-axis. We will select one graph. Let me refine the graph a bit. Now the horizontal axis needs to be logarithmic scale for it to actually look like a, now it looks like a low pass filter. And if you remember the high pass filter graph, it's just the opposite response of the high pass filter. Now let me put some markers in the graph. Okay, now so I have just put some markers in the graph. Now you can see that it is just the opposite response of the high pass filter. Here low pass means it allows all the frequencies below the cutoff or lower than the cutoff to pass, and rejects or attenuates all the frequencies higher than the cutoff. So high pass means allows all the frequencies higher than the cutoff to pass. Low pass means allows all the frequencies lower than the cutoff to pass. So just remember this, and it is not dependent upon which frequency we are working. Low pass and high pass filters are just filtering techniques which can work at any range of frequencies. Now let us move to band pass. Okay, so now I am going to plot for the band pass filter, and as I said, band pass is basically the mixture of high pass and low pass. So if you see the diagram in the right side, the first section is comprising of a high pass filter where the cutoff frequency is close to 16 Hz, and the next section is a low pass filter where the cutoff frequency is 265 Hz, and the bandwidth of this filter is 16 Hz to 265 Hz, and thus we call it band pass filter. So it allows a certain range of frequencies to pass through the filter and rejects all the frequencies which are outside of the bandwidth of it. So in the first section we want everything before the cutoff frequency to get rejected. That is why we are using high pass filter. So whatever comes after cutoff frequency, high pass filter allows that. And in the end section we have a low pass filter because we want something which will reject everything after the cutoff frequency, and that is why we need a low pass filter here. And the plot is fairly simple again. So Xe2 and Z2, Xe2 is basically the reactance for the capacitance of C2, 1 microfarad, and Z2 is the total impedance of C2 and R2, and Vout2 is basically the voltage at this point at the junction of the high pass filtering. Xe1 is the reactance of the capacitance C1, and the Z1 is the total impedance comprising R1 and C1. Vout1 is the Vout in here. So Vout2 is 2, or the input voltage multiplied by the resistance R2 divided by the total impedance Z2 of this circuit, the high pass circuit, and Vout1 is the reactance of the capacitor, Xe1 divided by the total impedance. That gives us the Vout1, that is the total output voltage from this full series of circuit, and the response is calculated depending on this Vout1. And now we are going to plot the graph having the x-axis as the frequency and the y-axis as the response in decibels. Now we need to convert this one to logarithmic scale, horizontal axis to logarithmic scale. Yes. So now I'll just add some markers in here. Okay, so I just added the lines for the cutoff here. For the high pass section, as I have said earlier, high pass allows everything after the cutoff frequency and attenuates everything before the cutoff frequency. So our cutoff frequency was 16 Hz. So here at this line you can see it allows everything after 16 Hz. So this is a logarithmic scale, so this is where 16 Hz is. So it allows everything after 16 Hz and attenuates everything before 16 Hz. This is the 3 dB point, and this is where the low pass filter is, and low pass filter allows everything before the cutoff frequency unlike high pass filter, and it attenuates everything after the cutoff frequency. So our cutoff frequency was at some 265 Hz. So this is the point where it is 265 Hz, and it is attenuating everything after that and allowing everything before that, and together they have a bandwidth from 16 Hz to 265 Hz. And now it is pretty clear, I guess, for you guys that why a band pass filter is always the best design for a preamplifier, because it gives you more control over the range of frequencies that you want in your system. So there is one starting point here and there is one ending point here, which is why band pass filters are more reliable in case of preamplifiers. That is why we'll use one band pass filter for our low pass filter design also, where we'll kind of attenuate everything before 20 Hz, and then from 20 Hz to our cutoff, whatever we'll set for the low pass filtering, it will allow everything and it will amplify everything, and then after that cutoff frequency it will again act as a simple low pass filter and it will attenuate everything after that cutoff frequency. So I hope after this response plot everything is clear, what is a high pass filter, what is a low pass filter, and what is a band pass filter. And as I said, this filtering techniques are not dependent on frequencies, it can be used in any frequencies, and especially low pass filters, it's just not that it deals with the low frequencies. Low pass filter can work with any frequencies, and the best example is that what we use in a class D amp. In the class D amp, the output stage you will have on low pass filter because it will filter out all the modulated signal that we impose at the starting. And if you want to know more about this, how class D amp works and how class D amp actually produces the sound, please do watch my Class D amp video where I talked about how a Class D amp works and also reviewed on Class D amp board with different voltage ranges and found out what is the maximum output power that a TPA3116D2 IC can give out. So I would say that's it for this video for part 1. I'll see you in part 2 where I will show you how I make the circuits in Easy EDA software and then I will design the PCB layout for this. Till then, stay tuned. Please do like, share and subscribe. See you soon. Bye bye.